Welcome back to Chem 4300. In this video, we're going to continue Chapter 5 on vibrational motion, and we're going to look at polyatomic molecule vibrations. Now, we're going to build on the material that we just learned about on how to do a normal mode analysis of coupled oscillators, and we're going to apply all of that to molecule vibrations. Now, let's just take a simple example of, say, a water molecule, how you might set up the problem for a normal mode analysis. So the first thing that we're going to do is we're going to pick a coordinate system that is fixed on the molecule with the origin at the center of mass and with the orientation of this coordinate system matching the principal axis system of the moment of inertia tensor. All right. This is important because if we pick that coordinate system, then as the molecule translates and reorients, rotates, that in that coordinate system we will see no effect of that motion on the equations, in the equations of motion. In other words, from the point of view of the principal axis system of the moment of inertia tensor, there is no translation, there is no rotation. The only thing that will be left will be vibrational motion. All right, so this is how we're going to set up the problem. In that principal axis system, so say for example for a water molecule, the origin would be at the center of mass. The water molecule will be oriented so that here you see it's in the AB plane and it's with the B bisecting the HOH axis. So this is the principal axis system of the water molecule. And we're going to define for each of the atoms in this coordinate system its displacement away from its equilibrium position. So for oxygen here, we're going to be looking at its displacement along the A axis, the B axis, and along the C axis. And we're going to call that displacement A to 1, A to 2, and A to 3. And that's the deviation of the displacement along the A axis, so AO minus AO equilibrium. Displacement along B, BO minus BO equilibrium. And displacement along C, CO minus CO equilibrium. Similarly, for the hydrogen atoms, for each hydrogen atom, we're going to look at displacement along A, B, and C. So we'll have A to 4, A to 5, and A to 6 associated with displacement along A, B, and C for, say, one of these hydrogen atoms. And for the other hydrogen atom, we'll have A to 7, A to 8, and A to 9 for the displacements along A, B, and C for the other hydrogen atom. So that means that we have 9 total coordinates to describe the motion of this molecule in this coordinate system, the moment of inertia, the principal axis of the moment of inertia tensor with the origin at the center of mass. All right, so keep that in mind. Now, of course, we're going to also, as we did in our previous analysis, we're going to convert from displacement coordinates to mass-weighted displacement coordinates. So we're going to convert all of these etas into q's by multiplying them times the respective square root of mass for the coordinate, the atom that they're describing. So we're going to have Q1 through Q9 describing the system. And then finally, we're going to get the equations of motion by using an expression that we learned about in Chapter 1, where we get the equations of motion from the kinetic and potential energy functions. So if we can write out the kinetic and potential energy functions for the water molecule in terms of these Q coordinates, then by taking the derivatives, the appropriate derivatives for this expression, we can get the set of coupled differential equations, which will then convert into matrix form. Okay, so again, this is bringing a lot of material together on what we learned in the identifying the moment of inertia tensor and its principal axis system, the equations of motion coming from potential and kinetic energy functions, and then all the normal mode analysis that we just learned. And we're going to apply all of this to looking at polyatomic molecule vibrations. Now, to write the kinetic energy out in terms of the mass-weighted coordinates, I'm going to leave this for you to check at home, but if you do that, you'll find that K can be written as the product of Q dot transpose times Q. So these are vectors. So this is vectors of the first derivative, the rate of change of the Q. So 1/2 times Q dot transpose times Q expanded out will give you the kinetic energy for the molecule. In the principal axis system of the molecule with the center of mass at the origin. Similarly, we can do a Taylor series expansion of the potential energy function in terms of Q. So V as a function of Q is going to be equal to V at the equilibrium positions. So this is the potential at the equilibrium positions, plus the next term, which is the rate of change of V as they deviate away from those equilibrium positions. But remember, since those are equilibrium, the potential energy function goes to a minimum there. So the derivative there is 0. So this term will go away. And then the next leading term is going to be the second derivative. And that term is going to be a derivative with respect to with respect to pairs of Q's. So it'll be a derivative with respect to Qi and then Qk, in the way I've written it here. So in other words, that's going to be the matrix element of a 3n by 3n matrix. Okay, that's how that's going to look. So I can rewrite the expression for the potential energy as V as a function of Q is approximately equal to V at the equilibrium positions, plus this term is gone. This term rewritten in matrix form is just going to be 1/2 Q transpose times this script V times Q. And this script V is just all of these derivatives, second derivatives with respect to Qi, Qk. So all of the matrix elements, the 3n by 3n matrix is this V matrix, is all these derivatives. So this is the analogy to the K matrix that we were using earlier. We're just calling it script V here. Now, once we have K and V, we can go back to this equation to get our equations of motion. And again, I'll leave this for you to do, but if you take those expressions here and here, then you end up with this expression here, which looks very, very familiar now to you. Just instead of K, we have a V, a script V here. And that matrix equation are the equations of motion in terms of the mass-weighted coordinates described in the principal axis system of the moment of inertia tensor for the molecule. So as before, the problem boils down to just finding the eigenvalues and eigenvectors of this script V matrix. You know that there exists then an eigenvector matrix which will transform this V matrix into a diagonal form. So just like before, we can do the trick where we insert 1 by applying L transpose times L into this expression, rearrange it, and we end up with an expression that looks like this, where now we've transformed our mass-weighted coordinates into normal mode coordinates. Here is Q, this double dot, the second derivative with respect to time. Here's Q, and lambda here now is the diagonalized form of the script V matrix here. So just as before, then this is a set of 3n uncoupled differential equations of motion, and they have solutions that look like this here, where we just have some oscillation times with some oscillation frequency, which is just simply the square root of the eigenvalues of this V matrix, script V matrix. And of course then the normal mode coordinates, the linear combination of the mass-weighted coordinates that gives us the normal modes, is just this eigenvector matrix times the mass-weighted coordinates to get the normal mode coordinates. Okay. Now sometimes in molecules you're going to find some of the normal mode coordinates will have identical frequencies. When we see that, we call those degenerate modes. Now, remember again that we picked a coordinate system that was in the principal axis system of the molecule's moment of inertia tensor. And since in that frame, any translation or rotation, if we're sitting in that frame, we're not going to see it all, right? Because we're moving with the molecule. So we expect then that some of those eigenvalues in this problem are going to be 0, because we included all the coordinates, right? So in the water molecule, we had all 9 coordinates, but that was in that particular coordinate system, and there's not going to be any rotation or translational motion. So we will expect that the eigenvalues associated with translation and rotation will show up in our solution as 0, as equations with 0 eigenvalues. So keep that in mind. Now, if we take our potential and kinetic energy terms, it's sort of useful also to see that once you're in the normal modes, that you can rewrite the potential energy form. And since these guys are diagonal, then they simplify, so they become a simple sum for the potential energy is just the sum of the eigenvalue times the normal mode coordinate squared. And again, this sum only goes to 3n minus 6, assuming a nonlinear molecule here, so we're leaving out the translation and rotational equations because they all have eigenvalues of 0. And the same thing here for the kinetic energy. You can show that it has this form in terms of the normal modes. Now, there are a couple of approximations we made along the way here that we have to keep in mind because, first of all, we did a Taylor series expansion of our potential energy function, and we neglected all the higher order terms, all the anharmicities. We learned about those earlier in the chapter. And of course, if we included those, then that's going to make the problem even harder. So one of the ways in which we treat those is we ignore them first, but then we can add them in later as something that will cause couplings between our normal modes. So normally our normal modes are all decoupled from each other, but if you add in an anharmicity, that will cause some weak coupling between them, and that's how generally people will account for that. The other issue that we ignored, or the approximation that we made, is that when we jumped into this coordinate system, which is the principal axis system of the moment of inertia tensor, we ignored the fact that that's not an inertial frame. That frame is rotating. And in that frame, there will be fictitious forces from being in that rotating frame. And those fictitious forces should have been included in our equations of motion. And in this particular case, the force that's going to be important is the Coriolis force. As those molecules move, the Coriolis force will cause additional issues. And so if we ignore those Coriolis forces, then we're not going to get exactly the right answer, but we can add them on later as a kind of perturbation. So we can stick with our normal mode analysis, but use sort of a perturbation to include the coupling between these normal modes that's caused by these Coriolis forces that we neglected in our first approximation. Okay, so generally speaking then, for normal mode analysis of a polyatomic molecule, we need to obtain the script V matrix, so the second derivative of the potential energy function with respect to the mass-weighted coordinates, find that matrice's eigenvalues and eigenvectors, and the problem's done, right? Just like before. So let's take a look at a full normal mode analysis, but we're going to stick with a diatomic molecule. Again, as we saw before, analytically, these problems can get hairy pretty quickly. So we can only sort of illustrate the concepts with some of the simplest examples. But it's very useful, actually, to go through this, even for a diatomic molecule. So let's take a diatomic molecule where we're in the principal axis system of the molecule. So it's along the A-axis. The bond is along the A-axis. And B and C are perpendicular to that bond. And we will write now displacements for atom A and atom B. So we will write eta 1, eta 2, and eta 3 for displacement of atom A along A, B, and C. And then eta 4, eta 5, and eta 6 for displacements of atom B along A, B, and C. Okay? And then we will convert those over to mass-weighted coordinates. We will multiply all of those times the corresponding square root of the mass of the atom that they're associated with. And then we will have our mass-weighted coordinates that we can then actually relate back, by the way, to the original problem that we looked at. So remember, originally we looked at this vibration, and we looked at it just in terms of the interatomic distance, r. And so if we write that, r minus the r equilibrium, that turns out to be just the difference between eta 4 and eta 1, which in terms of mass-weighted coordinates is just q1 over square root of mass 1 minus q4 of the square root of mass 4. So from that, we can take our original expression for the potential energy function in terms of the difference r minus re and rewrite that in terms of this difference. So I'm just going to replace r minus re with this term here. So I'm replacing that with this, and then expanding out that square, I get this term right here. And this is the potential energy function that we need to take the second derivative of to get our script V matrix. And you can just look at this and you can see right away that there's going to be only V11, so the derivative with respect to Q1 and Q1, which is V11, and that's going to come out to be just kappa F over M1. We're going to see that script 44 is going to come out to be kappa F over M4, and forgot here, there should be script 14 and script 41, because this is a symmetric matrix, will come out to be minus kappa F over the square root of the product of M1 times M4. So that comes from this term. This here goes to that term, and that comes from that term. And the rest are 0. Okay, that's just taking our potential energy function, writing it in terms of these mass-weighted coordinates, expanding it out, and then taking those derivatives for each one of those elements in the script V matrix, and you see that all of them are 0 except for these 4 right here. So writing out the full matrix equation for this problem is here. And you can see that primarily we have a lot of zeros along the diagonal, and there's only 2 here which are non-zero with corresponding off-diagonal elements. But this is our script V matrix for the full problem. So these are all of the mass-weighted coordinates here. And this is the problem that we have to solve. So we need to find the eigenvalues and the eigenvectors of this matrix. Now, of course, the reason that these 4 guys are 0 is because we set this problem up in the center of mass principal axis system of the moment of inertia tensor, right? So we put the center of mass at the origin, and we have the principal axis system of the moment of inertia tensor. So there cannot be any translation or rotation in this coordinate system. And so we see that already that the 5 of those coordinates have to have eigenvalues of 0, and 4 of them have already appeared in the way we've written out this expression here. So what's left is just these 4 terms. So if I go to get rid of the zeros and just focus on what's left to do, then you see that this is the problem that I have to solve to finish the normal mode analysis. So I take this matrix, my script V matrix, I subtract lambda from the diagonals, I calculate the determinant, I get my polynomial here, which I can find the roots, and I find roots of lambda equals 0 and kappa F over mu. So there's the other missing 0 eigenvalue. So I said there should be 5 eigenvalues that are 0. We just saw 4. When we do this, solve for the eigenvalues with this determinant, we find the other 0. And this non-zero eigenvalue is the eigenvalue associated with the normal mode vibration here. And this mu, of course, is the reduced mass we had before. I'll do a little rearranging of the reduced mass here, and then I'm going to rearrange it so it looks like mu is equal to M1, M4 over capital M, where capital M is the total mass. This will be handy here in what comes next. So, as I said before, 5 out of the 6 eigenvalues are 0, as we expected, and those are associated with translation and rotation. And 1 of the 6 is associated with vibration, and it has a frequency of square root of kappa F over mu, exactly what we had found before, and the normal mode solution is here, just like we've found. Now, to get the get the eigenvectors now, then what we're going to do is we're going to go back to our equation. We're going to take our eigenvalue, we're going to subtract it from the diagonal, and we're going to expand out these equations here. So that times L11 plus that times L14 equals 0. That's one equation. That times L11, that times plus that times L14. That gives us the other equation, but both those equations are identical, and they simplify to a relationship between the L11 and L14 elements. You see that they have to be related according to this equation. And of course, we also insist that the eigenvector is normalized. So we'll write down our eigenvector unnormalized here with some undetermined coefficient b with this relationship between the 2 elements. And then if we normalize it so that that L11 squared plus L14 squared square root equals 1, then we solve for b, and we get the final eigenvector here in terms of mu and M1 and M4. If we do the same thing for the second eigenvalue, remember the second eigenvalue was 0, but we can solve for its eigenvector, and we'll get this eigenvector here after it's normalized. So bringing it all together, then we see that the normal modes, Q1 and Q4, are related to the mass-weighted coordinates, lowercase q1 and q4, with this multiplier here, the eigenvector matrix that gives us the linear combination to go between the two. Now, this q1 coordinate is the one that's associated with the vibration, and we can take that coordinate and we can multiply this times q1, that times q4, and add them together, and we get this expression here. And that's the expression for the normal mode. And you, of course, remember that this q1 over square root of m1 is just the displacement. So I'll just go ahead and replace these guys with the displacements. But you also remember that that actually is the distance between the two atoms. And so we have that simplifying to this. So we see that the normal mode q1 is just simply related to the internuclear separation, of course. And so the oscillation of that internuclear separation is just proportional to the normal mode frequency with the 1 over the square root of the reduced mass. And that's, of course, has this cosine dependence with a frequency that we just determined. Okay, so that's the normal mode analysis on this very simple case. Now, we still have actually one other normal mode here. This is a normal mode associated with one of the translational degrees of freedom. But of course, remember, we're in the frame where we're locked on the molecule, so there should be no translation. But if we look at that term, if we go back to the expression and we expand that out to get that Q4 term, we get this. We can actually just double check here that everything is working out fine. We can rewrite that in terms of the displacements, and then rewrite that in terms of the actual coordinates here. And then looking at this, if you remember the definition for the center of mass, and we know that the center of mass should be, when they're at equilibrium position, should be equal to 0, because the center of mass is defined to be at the origin. So when they're at their equilibrium positions, the center of mass should be at the origin, but when they're vibrating, it's not, right? So you can see then that we can use these two expressions to simplify our Q4 expression to this expression, which tells us that Q4 is related to the change in the center of mass. Okay, Q4 is simply the position of the center of mass along the a-axis. But remember, lambda 4, the eigenvalue for Q4, is 0, right? And so that means that the equation of motion for Q4 is Q4 double dot is equal to 0. And if we have an initial condition of no motion on Q4, or no motion on the center of mass, which we would have if we started out in that frame, that means that the center of mass cannot change with time. Obviously, it can't change because the eigenvalue is 0. So that means that for all of those coordinates, normal mode coordinates that had the lambda equal to 0, the ones associated with rotation and translation, sorry, that means that while the molecule vibrates, that there's no change in the center of mass or the orientation of the molecule. So anyway, that is the sort of full analysis analytically, normal mode analysis. And the most important thing is that it sort of makes you more familiar with all the concepts of normal mode analysis. And generally speaking, you'll probably be using some kind of software to do more sophisticated normal mode analysis of molecules. Later in the class, when we do quantum mechanics, we'll learn how to get the potential energy from the Schrodinger equation and the Born-Oppenheimer approximation, and full-blown quantum chemistry programs will give you all of these kind of normal mode details. But now you'll know sort of how it comes about. So that's it for this, for the end of the chapter here. And there's a nice old video on vibration of polyatomic molecules you should watch. And then this is just a link to some just sort of review material for the entire chapter.